Hello and welcome to episode 1 of my data structures and algorithms series. If you missed the intro episode, be sure to check that out linked right up here, and be sure to get subscribed to me so you don't miss any of the future videos in this series or any of my other ones. So today we're going to be talking about time and space complexity. This is the core feature of data structures and algorithms really, especially when you're looking at algorithms, as it's really what you're trying to optimize for all the time. What time complexity is a measure of how long your program will take to execute as your input size grows for your algorithm, and what space complexity is how much memory your program is going to use as the size of your input grows as well. So you can think of this as being closely related to the concept of limits in mathematics. We're going to start off by talking about time complexity because it's something that you see asked about a lot more often than space complexity, at least in my experience. So when you're measuring time complexity, what you're looking to do is essentially say how many steps does this program have to take for every time that our input grows. So here, for example, in this first example, we have a function that just prints out every element in the array by looping through it. So here we can go ahead and correlate as our array length grows, how many steps is this going to have to take? If the array is length 1, it's just going to have to print out one element taking one step. 2, it would have to take 2 steps to print out both elements, and so on and so on. So this algorithm we can say has a runtime of O of n, because n, it being the length of the array, will determine how many steps we have to take. So now that we've seen a quick example, let's take a second to talk about the actual mathematical definition of big O, because it's going to be what we're using this entire time. So in its pure mathematical definition, the big O of an algorithm is a top bound, saying that the algorithm will never take longer than that to run. So while we said that this had a big O of n, it would also be correct to say that it had a big O of n squared, or something like that, because we know that it will never take longer than that number of steps to run. It would just be less specific. In math, there's also a concept of big omega, which is sort of the opposite, and it says this is a bottom bound for this function. So we said that this has an big O of n. We could also say it has a big omega, even though we know it's going to be n in this case, because we know it's going to take exactly that number of steps. We could also say that it has a big omega of 1, or square root of n, or something like that, because we know it will never take fewer steps than that number to execute. So finally, we have the concept of big theta. So big theta is sort of when the big O and the big omega are equal to each other. It's saying this is a tight bound. We know that this algorithm is going to take this long. And practically, in actual sort of industry and things like that, we never really see these definitions of big O and big omega. Because they're just not that useful most of the time, because most of the algorithms you're going to write have a pretty defined tight bound on how long they're going to take. So we still use the big O notation of saying big O, but what we actually mean in a mathematical sense can be equated to theta. So we understand that the basics of big O is that it's calculating how many steps it's going to take as our input size grows. But let's go over some common rules for it so we can get a better understanding of how to use it. So the first thing here is when we have some sort of constant factor. So here you see we have a similar loop to before, but first it will assign a variable which is equal to the array indice plus 1, and then it will print out that variable. So if we go ahead and count our steps, you'll see that for an array length of 1, this would take 2 steps. For an array length of 2, it would take 4, and so on and so on. So your immediate instinct might be to say this has a big O of 2n, because that's how it grows, but this is actually going to be wrong. This is actually going to have a big O of simply n, and that's because when we're calculating big O values, we always drop the constant multiples. And this is because these constant multiples are not actually a useful thing to do and to have, and they don't actually give us any information on how our input size grows. So now before we talk about the next rule, it's important that we remind ourselves of some of the common runtimes and how they compare to each other. So here I have a list of some of the most common runtimes that you'll see for algorithms, but be sure to remember this is not an exhaustive list, because there is no exhaustive list of runtimes. Runtimes can be of pretty much any form as long as they follow the 2 rules that we're talking about here, and they are just sort of giving you a mathematical function for how your runtime grows. But some common things you're going to see are 1, which is just constant runtime. No matter how big your input size is, it's always going to take the same number of steps. Then log n, which we'll get to a little bit more in a second. And then we have square root of n, which we saw before is just linear, and then n times log n. And then you'll have something like n squared, or 2 to the n, or n factorial. And generally, just what you want to do is have your algorithm go as far in this direction as you can possibly get it, because smaller runtimes are always better. Now that we understand that common hierarchy, we can talk about non-dominant terms. So in this example function right here, first we run through the entire array, and then for each item in the entire array, we run through the entire array again. So if we think about it, this first part here is going to have a runtime of n because it's going to grow linearly, and this second part here is going to have a runtime of n squared because it's going to grow at that rate compared to n, because for each time we go through the array, we go through the entire array again, essentially multiplying n times going through the array times n elements of the array that we go through each time we do that. So this, your immediate thought might be to say that this has a runtime of O of n plus n squared, but this is actually wrong, and it's just going to have an runtime of O of n squared. So the reason for this is that we drop all of our non-dominant terms because they don't add any interesting information. So if you think back to limits in mathematics, it's the exact same rule there. Because the n squared grows so much faster than the n, the impact of the n is going to be minuscule, and there's no reason keeping track of it. With that, we've covered all of the basics of calculating runtime, and you should be able to calculate runtime for pretty much any function. Your ability to do that is just going to grow a lot with practice, so I recommend seeking out some practice problems for that just to build on your skills. But now we're going to talk about some common mistakes that people make and questions that people have. And the first is when you should multiply runtimes. So if we look at our same example function from before, we can see two instances here. We have a stacked thing in that we do this loop and then we do this loop, and we also have something nested, which is this loop going into this loop. So when we have stacked functions like this, we can essentially add the runtime. And as we saw before, whenever we add runtimes, we can essentially just drop whichever one has the lower runtime because it's not going to have any impact. So this is important to note because of this, you can do any sort of preprocessing that takes less time than whatever the sort of highest runtime thing in your algorithm is, and it's essentially free for your runtime. It won't have any impact. So because of this, you can often lower your runtime just by breaking things up and doing them in steps instead of doing them in one big nested thing. And then on the other hand, we have nested things right here. So we have these two for loops nested. And we note this first for loop is going to run through n times, and so is the second one. And since they are nested, so one is happening for each time the other one happens, we can go ahead and multiply those together and say that that is going to have a runtime of n squared because this first one has a runtime of n and the second one has a runtime of n, and n times n is n squared. So now the next question people often have is, when do logarithmic runtimes come up? Because when you're dealing with big O, you're going to see logarithms a lot, but logarithms aren't something that you think about probably a lot in your everyday life. So if we think back to math first of all, we can say, what is a logarithm? And a logarithm is simply the opposite of an exponent. So in a logarithm, as the input to the logarithmic function rises exponentially, the logarithm will grow linearly. So here, if we think about this in this scenario, so we have this little function right here, which does a binary search, and we can compare the runtime of the function with the input size of n. And as that input size grows exponentially, the runtime of this grows linearly, so it is a logarithm. So if we think about why that works, we can take a look at this function. So what this function does is a binary search. So if you have some sort of sorted list, which is what this is working on, what this is going to do is first it's going to check the midpoint, it's going to compare that to your input, and if your input is higher, then it's going to ignore the first half of the array and then just do the same thing again. So when you're doing a binary search, you're essentially having your input each time. And because of that, it can very easily be modeled as growing logarithmically because you're essentially exponentially searching through the list, which is going to be much quicker than if you were just linearly scanning through it. So another important thing to note with logarithmic runtimes, you may notice here that I wrote this as log base 2 of n, but you will never see log bases inside of logarithmic runtimes. And that's because the base also simply doesn't matter. If you compare the growth rate of two different logarithms with two different bases, they're actually going to be linearly different from each other. And as we mentioned before in our first rule, if you have any constant that affects your runtime, you simply ignore it. So the base of your logarithm doesn't actually matter, and that's why you will just see log in your runtimes rather than a certain base. Next important concept is the runtime of recursive algorithms, because recursive algorithms will come up a lot and they can be a little bit tricky to think about in a runtime sense. So here I have a really bad Fibonacci function, just as an example of a recursive function, and we want to calculate its runtime. So this is a little tricky because the number of times that the function actually gets called changes based on the size of our input. So you'll see here how this works is we have our two base cases right here, and then If we are not in our base case, then we make 2 calls back to this same recursive function. So when we're dealing with something like this, it's easy to think about it as modeled by a call tree. So if we take a look at this and we use 2 as a sort of base for how our input size grows, you'll see on this first level we make 2 to the 0 calls, then here we make 2 to the 1 calls, here we make 2 to the 2 calls, and so on and so on. So because of how this is modeled, you can get a very tight runtime on this by using some actual math, and you'll find that it's actually like 1.68 to the n or something like that. But a shortcut for most recursive functions that's going to give you a good enough answer most of the time is just to do the number of branches to the call depth of your tree. So here in this case, that's generally going to be big O of 2, because we make 2 recursive calls on each time, to our depth, which is going to be n. So here we can say this function has a big O of 2n. Even though that's not perfect, if we think back to how big O works, that's going to give us a decent upper bound and will be acceptable in. Now, the final rule I want to talk about, and this is really important, and I see a lot of people mess this up, is how to approach what happens when you have 2 different inputs that have different sizes. So here in this function right here, I go ahead and print out every combination of an element of array 1 and an element of array 2. So your immediate thought here is, oh look, I have 2 nested for loops, this probably has a runtime of O to the n squared. But that would be very wrong, because we never said that these 2 arrays have the same length. And if they have different lengths, then that's going to be very different. So here also I'm going to bring up an important concept, and that is to say that there's nothing special about the letter n. We just use it because it's a easy thing to put as a stand-in for the input size, but you can use anything there, including an entire word to represent the runtime of a function, or just any letter variable that you want. So here I said that the length of array 1 is going to be represented by a, and the length of array 2 is going to be represented by b, and then we can simply say this has a big O of a times b, because for every run through of our a array, which is this big for loop right here, we run through the entire B array. So with that, I've covered everything I wanted to say about time complexity, and we can now take a second to talk about space complexity. Space complexity is essentially the same thing as time complexity, but talking about how much memory you're using rather than how many calls you're making. So for something like this, when you are not allocating a new array or doing anything like that, or you're just keeping track of a few static constant number of variables, like for example, if you're finding the maximum value in an array, your space complexity is just going to be 1 because the amount of memory you use is constant regardless of what your input size is. So then if you're doing something like copying an array, then you're going to have a big O of n because your amount of memory used is going to grow linearly with your actual input size. And then the final important thing to keep in mind is what happens when you have a recursive call stack like we had in our function earlier. So there you might think, because there are essentially going to be 2 to the n number of nodes in memory that we have to keep track of for our input, then it might be 2 to the n. But if we take a look at how that function actually works, this is actually just going to have a runtime of O of n, because we're not going to have all of these nodes allocated in memory at the same time. As we build up from the bottom on our bottom level right here, these will stop being kept track of because they're just going to be numbers, and then that, and then that. So we're only going to be using a O of n amount of memory for that function. That covers everything I wanted to say about time and space complexity. If this is your first exposure to this topic, don't worry if it doesn't click right away and there's some parts that you don't get. Really what you have to do at this point is just practice applying these things by finding the big O values of different algorithms, and eventually you will get it and you'll be able to recognize different patterns and pick up on things like that. So as you just practice more and more problems, you will get a lot better at this, so I highly recommend you seek out. There is a lot of practice available online. That is going to be all from me for today. I hope you enjoyed this video, and I hope it gave you a good foundation that we can build on in the future videos. So this is still an introductory topic, but it is also probably the most important thing, because if we didn't know how to measure our time and space complexity, we wouldn't have any sort of metric for efficiency, and therefore we wouldn't be able to mathematically think about what sort of algorithms and data structures are going to be the best fit for the sort of problems that we're doing and do things the most efficient way possible. So I hope you stick around. Be sure to get subscribed to me so you don't miss any of the future videos. And next week, we're going to be talking about arrays and how to traverse them, as that is really the basis of a lot of the different data structures that we're going to be talking about. So leave a like on this video if you enjoyed it, get subscribed to me again, and I will see you in the next one. Goodbye.